I go to English.
All right, let's begin. So today, we actually are going to do some work. I apologize. But I mean, I feel like we don't want to have you come to a pasture and not feed you. You know, like we got to give you some mathematics if you're here.
I know, like, no, wait. Oh, wait, are you going to do this as a trick?
Shut up. I didn't go to the bathroom.
So, this is good. I hope you guys realize what I'm making you do here. In fact, these are important enough and happen often enough that we're actually going to declare these with a name. We're going to call these like the double angle formulas, right? But I hope you never, when it comes time to like put those in a box, I hope you're not like storing that information somewhere in your head. It's different from the place where you store the sum and difference identities, right? They are an immediate, and you just saw it, they are an immediate consequence of the sum formulas, aren't they? So don't be thinking like, oh no, 3 more formulas to memorize. I mean, what, you know. In fact, there's no formula you should memorize in memorize in the capital M sense, right? Everything is rederivable from first principles. I hope that's a strong idea that's come through. So I have nothing on this first slide to offer more than our warm-up doers provided. Now I will say on the second one, there are maybe 3 equally simple ways of writing this. So the cosine double angle formula, nobody can decide which is most useful. So in the context when you're using it, you might choose to use one of these or the other, right? And the tangent of 2u is what was said on the first slide. So all these are what you just said on the first slide. You guys derived them, and now I put them in a box. But you don't need to write down any boxes today. I have a crystal. So
What he said was so great.
What do you say? Oh, hell no.
I'll take that.
Yeah, I'm right by the door, so I'm ready.
What he said was so relatable though, because on like the rotating.
What a rebel.
Like I forgot all the formulas. So I literally re-derived them as I was taking the test. Oh, I was getting one at my place.
Oh, Mr. Chase, you pulled up all the stuff.
Thanks, bro.
Everybody's so pretty.
Hi, yeah.
all right, hey, what's up, everybody? Listen, so that's the sound of hard stop. Okay, there are 2 sides, like everything that a man or a woman needs to know about trig. Units 4, 5, and 6, it's like everything. Now, Mr. 2005, Paul Dawkins is the one who made this, and I just stole it off the internet from him. Well,
He did. He was
I produced like a radio.
If we can do it,
But I did put in an order to the copy center to make something that I got.
Oh, did you pay with it?
that's what we do for all our essays.
Yes. So you can pay for your own presents.
Gee,
All right, let's just bring it real.
Wait,
right
so
down.
we paid for our own re-gifted present from podcast.
Yes. I am involved, though. I want you to know. I did download it, and I did order for it. Okay. And they didn't even do that great a job of centering it. Maybe it's supposed to be produced on A4 paper or something. So, yeah, there are lots of interesting things on here that we've known and derived and thought about lots. And there are some things that he offers because he's not me. That he offers that we don't necessarily emphasize in this course, like Mollweig's formula. What is that? Law of tangents. You didn't even know there was one, but there it is. Okay. So you're not responsible for those, but it's just a little bonus, something extra, you know. Is this one right here, guys? Are the double angle formulas? Can you find those somewhere on there? Are those on there?
I find them.
You found them?
Yeah.
Good. Notice there again that the cosine double angle formula has 3 different equally interesting and useful forms. So, but again, all of these, everything on this whole yellow sheet front and back, like you should have like a.
Oh, I found them.
should be able to rederive, right? You shouldn't be able to. Okay, so good, you're welcome. Now, you might still want to write down how these things are derived. Like I'm gonna prove some of the results today. By the end of the day, though, we're gonna not have any more formula trig identities like to give you. We're gonna be done. We're gonna have given you them all. I'd like now to develop something called the power reducing identities, which don't appear on that sheet by this name at least. I'd like to first start by considering the cosine double angle formula that comes in this form. That's a result that we just derived a second ago. And if we solve for sine squared, then we get this. And that's the power reducing identity for sine squared. Now the reason that's useful, I want to make sure you're clear, like, okay, if you're like, neat. But think about, there are two contexts I could think of using this in and maybe caring about using it for. One would be, like, say someone asked you to graph y equals sine squared of x. At this point, I think you'd be like, I don't know how to graph sine squared of x. Don't know how. I've never done it before. But you do know how to graph this, don't you? And it's the same thing. So, I don't know if you knew this, but sine squared of x is just a horizontal shrink by a factor of a half of the cosine graph. And what else is going on there? Vertical translation up by a half. And the amplitude will be one half, and there'll also be like a flip over the sides of the lattices, right? So you could actually graph that if you want. The other kind of time I feel like I might want that is in calculus. Turns out we can't in sine squared is something is not easy to deal with in calculus. And it turns out the expression on the right is. So I'll just say that. A similar formula can be gotten for cosine squared, the power reduction identity. That is, if you see a cosine squared, can you like reduce it to things that are just cosines or sines? And if you take the second cosine double angle formula that we derived on the previous slide, the other form of it, then solving for cosine squared gives this. And tangent squared we'll get in the following way. We'll just do sine squared divided by cosine squared on the previous two results that we just derived up above it. So, and then you can put them in a box. Do those appear on the L sheet somewhere? They're not called the power reduction identity, so this is actually a little bit of an interesting question. They're called the half angle formulas? What's up with that? But they do appear on there. I'm not sure why they're called the half angle identity. What about the theatrics thing? After first teacher's So that's how those are derived. They're come from, we present these in this order so that you can see where these come from, right? Double angle formulas, we presented those to you first because they're easy to derive from things you already know. And then this we can derive from the double angle formula for cosine. And then the next slide I'm going to derive something else called the half angle formulas, at least what I'm calling the half angle formulas from these. Was that good? Or were you good? Wave wildly if you didn't watch that. Oh. Okay. That. Oh. Yeah. Yeah. Those are the half angle identities according to Paul? Yeah, I guess so. They are really kind of the same. Yeah. There's not much to do. I'll show you. Yeah, are you waving vigorously? Are we done? Okay. Maybe else? Give me a second. So yeah, let's derive the half angle identities, which yeah, Paul already thinks we have them, and he's right to some extent. There's really not much work to do. If you take the identity on the previous page for sine squared, did you see that? It was sine squared of x equals 1 minus cosine of 2x over 2. Did you see that? So if instead of x we use u over 2, I want you to see this. If you use, instead of x, you use u over 2, then what that says is this, right? That the cosine squared of u over 2 is 1 minus cosine u over 2. That's really just the power reduction identity from the previous slide with like a u over 2 in there instead. So I think what we have here, do you see it, is sine squared of u over 2 equals 1 minus cosine u over 2. Taking square roots gives us what I would probably call the half-angle identity. I think that's how your book represents it. But it is, do you see why they really are the same thing? The power reduction identity and the half-angle identity is just like us taking square roots. That's all, kind of. Now, to be clear, this is not a plus or minus that's resolved in the following way. It's not like a plus and minus. It's a plus or minus. You know that the sine of an angle, even if it's a weird angle, is either positive or negative. It's not simultaneously both. So please don't write, when you solve an actual problem that involves this, please don't write plus and minus. They're not two answers. So choose whichever one you know to be appropriate depending on what quadrant that u/2 angle lies. So I hope you see the usefulness of this. This gains us access to finding the sine of, say, like 22.5 degrees, for example. We can find that exactly, very quickly. The sine of 22.5 degrees is also known as what over 2? Yeah, so we can find the sine of 45 over 2. 45 degrees over 2. Right? Because the sine of 45 degrees over 2 would be plus or minus, well, which is it? 22.5 degrees. You don't know much about it yet in your life, but you do know its sine is positive, so, okay. So it'll be positive. The square root of 1 minus cosine of 45 degrees over 2, which is something you know. So you can see already how this is going to be useful to gaining access to angles you've never been able to take the sine and cosine of before. Similarly, we can use the cosine power reducing identity from the previous slide and just take square roots and give a very similar result, just with a plus instead here. Tangent, I'm going to use this kind of hack again. I'm going to do the two results we just derived. I'm going to stack them on top of each other. And if you clean that up a little bit, you get that. And actually, we can clean it up even more. This is actually a fine place to stop if you really wanted to. And you could call that the tangent half-angle identity. And that is on your sheet also, I think. It's just, like I said, it's just squared on both sides, right? But you can actually clean it up a little more if you really want. If you take under here, it's almost irresistible, right? You get a 1 minus cosine over 1 plus cosine. It's almost irresistible. Maybe we multiply the top and bottom inside the radical by like 1 plus cosine over 1 plus cosine, maybe? If you do you agree that you would get this? If you multiply top and bottom by 1 plus cosine? Yeah? You might be thinking, well, yeah, I guess I agree, but why would we do this? Well, the top is sine squared. I don't know about you, but I see a square root with underneath of it something squared divided by something squared, yeah? Boom, baby. Right? So that's actually a really nice cleanup on that. I'd like not to have a radical in my life if I don't have to, so there you go. Now, you might have thought, actually, my first thought, Mr. Chase, was to multiply by 1 minus cosine over 1 minus cosine. That was what my heart's desire was. And if that was you, I have news for you. That's cool too. You'll get similar results here, and you'll get this formula at the end. And you might be thinking, how cavalier to drop the plus or minus, but I promise you can drop the plus or minus. Time doesn't allow us to but you can think about it some more. Just try some values. You'll see that the sine of tangent of u over 2, it's sine, S-I-G-N, plus or minus. It always agrees with the sign of these expressions. So again, these are things that are on the yellow sheet. These are things that you can just write down the final result. But I always like to share the reasoning with you. There's nothing at all that we want to talk about in math that we don't derive from first principles, right? Let that be said. Okay. I still need to put these 3 things in a box, boom, boom, and boom. But the derivation is before you. Any other thoughts or questions about that? No. You've already even thought about why it might be useful a little bit, maybe. I guess let's return to that question too. Does it make sense why he doesn't have, this guy Paul, doesn't have both the power reduction identities and the half-angle identities on there? I mean, they're really kind of the same thing to some extent. Yes, of course. Anyone still need that? Jeffrey, did you get all that?
I'll redivide them one time.
Let's see how that goes. All right. There they are in a box, everybody. Yeah, and there was much rejoicing.
Unless you want to stand and pose for a picture.
I don't know. It's up to you. This is the way. These are in your book. I think in this form. On the sheet, if on the sheet, that's fine too. Whatever you need to do. You might like how these are written and want to write them down, but okay. Whatever. There we go. There ends all the trig identities that you'll ever learn. Okay. And yes, you need to know them all. Okay. The yellow sheet is nice, but it will not be provided to you on the test. All right, solve this equation for me, please. How do you do it? What do you do? How can you do it? Zero is the solution after. Are you guys singing? You want to come sing for us?
Merry Christmas!
Deck the halls with boughs of holly, la 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 la. 'Tis the season to be jolly, la 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 la. Don we now our gay apparel, la 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 la. To the ancient Yuletide carol, la 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 la.
Thank you guys. Are you going to Miss Gaffney's today? Sweet.
Julian. I want to see Santa down.
Aren't they so good? All right.
I got 0.
How's it going? You're like, could you please move? Follow along.
You got it. Sit down. Now you have 5.
What'd you do? What are you doing? How's it going?
Now you have 5. Now you only need 2 more.
The first move is the most important. What is
I
it?
need 3 more.
Or break it, either one.
What's sine of 2x, also known as?
So now you only need 1.
By the way, they're on the video too. Isn't that great? Okay. You can go hear them again. If you watch the video.
Oh, yeah, my mom did.
Oh, yeah.
My brother is here, so she.
That was one of you. Those people was your brother.
Wait, yeah, it's a tall, lanky, awkward guy.
You have to be ready.
I don't think I ever had him.
Did you say hi?
You didn't run up and give him a hug though. How's this going? I mean, the first part, this is the big move. The rest is kind of like a problem. Actually, it might even be the exact problem we've done before. I don't know. So what do we get? Sine x equals 0, implying that x is either 0 or pi. Or cosine x equals 1/2, implying x is equal to pi over 3. Or 5 pi over 3 on this interval, right? me how you like that. Like you said, this right here is the important piece that you couldn't do before.
You started twice.
They don't want to hear a joke. You good?
Oh, I like your hat. You know what? Really, looks kind of similar to that. I am the joke. Oh my God, mine was shiny. Mine was my advice.
Why?
Outdone.
What'd you get for
Are you done with that one? Are we good? Let's focus. Are you ready for the joke? Sure. Are you ready for real?
Yes.
Oh, for real? Okay. It's a joke. Okay, here we go. Why couldn't, this is the joke, everybody. Why couldn't the identity sine 2x equals 2 sine x get alone? Because it is, yeah, an astute trigonometry student would probably notice that it is missing something. That's right, it needed a cosine.
That was cute.
Oh man. Oh man. Woo! That's hilarious.
You should have had the sounding of
Oh yeah. Thank you. But seriously, thank you. The sitting ovation. I haven't. That's amazing. Okay. All right. Back to your regularly scheduled program. Now, I really like to just have you stare at this until it just becomes obvious. There's really almost no work to do. Until you stare at it until you realize that it's fairly self-evident. I'll direct your attention maybe to some of the formulas we learned today. Don't worry. There's one of the cosine double angles formulas I think is going to help here. And again, stare at it until you just kind of see it pop off the page. Do you see it? I mean, I guess the big realization you need to have is that the left-hand side could also be written as cosine of 2 times 3x. How does that look? I mean, am I right that just kind of once you recognize that 6 is 2 times 3, is just done? It's kind of done. It's pretty done. Look at that formula. Let's see. Let me see the formulas we got here.
Why?
Cosine of 2 theta is, we already derived this today, 2 cosine squared of theta. So 2 cosine squared of that thing. What am I supposed to do? Oh yeah, minus 1. What? Oh, that's the thing we wanted to prove. Okay. Do you see what I mean? It's hard to even explain more of your thought process than that. I mean, I think you even show more work. I don't know how. Okay, so are you comfortable with that? Like I said, at first it looked messy, but then, as the amazing mathematicians you are, you look for and made use of structure. That's what you did.
You have to give it a try. The rectangle. Did you really practice this?
This one looks like fun. You might call the thing we're about to derive the sine triple angle identity. Okay? Yeah, I mean you could You could also ask for, when you're done with this, like the sine quadruple angle identity, right? Or the quintuple angle identity. But we just gotta stop the madness somewhere. So we will actually prove this statement here. We will prove this. But we're not gonna put it in a box, okay? If you ever need it, which is I think gonna be rare, you can just rederive it. Okay. So I don't know that you will need it. I mean, once you have the double angle identity, you know how to bootstrap to get anything you need, right? And the sum and difference identities.
Wait, where? That's not the.
It's. I didn't do anything yet. Sine of 2x plus x.
Oh!
That's the same thing as what we're dealing with, isn't it?
Yeah.
Pay attention. Sine of something plus something. We did like an extensive study on that.
I know. Now you have to do
Sine of the first thing,
yeah.
cosine of the second thing,
What?
plus cosine of the first thing, sine of the second thing. Sine 2x is sine 2 sine x cosine x. Cosine 2x is, well, which one would you like to choose? Hey guys, maybe we just kind of kill the side conversations. Okay. That's not nice. Can you tell me what formula you like to use to deal with the cosine of 2x? There are 3 of them, right? Which one would you like? Keep in mind the target expression.
1 minus sine.
Maybe the one that has sines in it. Yeah, 1 minus 2 sine squared.
Yeah.
Just because, I mean, any of them, I think any of them would bring you success in the end. It would be fine. It wouldn't be a mistake to do the other ones. But I think if we have the sines in mind at the end, then maybe we want to try and work on getting sines everywhere. In fact, I've got a cosine squared right here, so maybe I want to do that right now too. Here, make that a 1 minus sine squared. Over here, I might start multiplying this out here. What is that? Sine x minus 2 sine cubed. And I'll multiply this out to, do you see it yet? 2 sine x minus 2 sine squared. Can we collect some like terms there? We got, sorry, sine. We got a 2 sine and another sine x, so that's a 3 sine x. And what's that? That's a negative 4 sine cubed. Do you see it now?
I see it.
So, I just want you to be comfortable proving stuff in general. And you do have a new bag of tricks here to bring to the table when it comes to proving things.
All real numbers.
Let's see if we can at least set up this last problem. I know I'm not really sure what's on here, but I promise that you would be able to use this half angle formula to do some things too. So,
Guys are eating my
is this good?
selfish.
The sine of 5 pi over 12 is one we did yesterday using the sum and difference formulas. I want to show you that you can get it using the half angle identity nicely today too. So sine of 5 pi over 12 is also known as half of what angle?
6 pi. No, 10 pi.
Yeah. So 10 pi over 12 or 5 pi over 6 would be a great way to say it. And isn't that an angle you know and love? All right, then the half angle formula says, by the way, before we even get started, is the sine of 5 pi over 12 a positive or a negative number? Even though you don't know very much about that angle, you do know its sign is going to be positive. Yeah. So is it going to be plus or minus? It's going to be plus. The square root of something. I forget. This is on that one of the formulas I gave you earlier. The half angle identity for sine. It goes 1 minus cosine of 5 pi over 6 all over 2. And that's something that you know how to evaluate, right? simplify, call it a day. All right, homework 7 for 2017, please. Okay.
Did you win one? I was like, dang.
Thanks, Mr. Chase.